Hello. Today we're going to review something that'll help you finish up the uh, kinematic flow fields lab. I just want to talk about some of the conclusions that we should be able to get to based on this lab. So when you turn it in, you're going to have everything written up. It's got to be super neat, super professional. We've done the answers together. You need to show me the level at which you're professional. So complete answers, really neat. Spend the time to make it look fantastic, okay? So let's start with the screen share, as always, and pull up my little blackboard. And we're just going to talk a little bit about how these thunderstorms work. So the idea of the one where I've got translation along with divergence. So the key thing is when I'm drawing all these arrows in, and I'm looking, and I'm just, for the sake of simplicity, I'm just going to draw 4 arrows. Okay, so here's the 4 arrows that we're drawing for divergence. And then we said we're adding to it the translation arrows. So the key thing that matters is we want to have 3 options. Which is greater, the translation or the divergence, the magnitude of each. So when I put a small vector like this, and then I come up with the red net vector connecting the loose ends, as we did in class, I get one that goes over there. Now, if I had used a larger one, do you see that the red arrow doesn't really change by much? It goes a little bit different. It goes off in a different direction, but it's still basically going to the northeast. Okay, now the same is true if I were to take the vector here, go with the small one, and then the red arrow connects like this, right? And if I had used the longer of the arrow on the end here, so if the dark green had been bigger, then the bright red would have been just a little bit longer. It's still pointing in the same direction, right? So the only place that really matters is on this guy going in the back side of the storm. So if I take a look at the green and I do a small arrow, then which way does the red arrow point? The red arrow points that way. But what if I took a longer arrow? I guess I did the bright one. Which way does the red arrow point now? Now it, whoops, sorry. Now it points, let me get this right. The red arrow points in the other direction. It's going to go in that direction. So instead of anvil material going off to behind the storm, you have it going off ahead of the storm. So that side, this guy over here, this is where it really matters. Where does that anvil debris go? Does it go backwards behind the updraft into the winds, or does it go downwind? Okay, so what that says is this. The amount of divergence versus translation matters. Now, mass continuity says this. So let me do this for a second. Let me get rid of this. Mass continuity says this. I've got an updraft going up, and then at the top of the updraft, there's going to be divergence. Now, the divergence is going to create an anvil going off in different directions. So I can kind of think of this as an anvil forming this disk around the thunderstorm. Now, if the upper level winds are going in this direction, then I'm going to get most of the debris going off in this direction. It's not going to be perfectly symmetric. The updraft, the air will go up in the updraft here, and then a lot of it will go this way. Some of it will diverge and try to go into the winds. Well, I want to look at how this arrow compares to the winds aloft, that arrow. That's really what we're talking about. So what happens if there's more divergence than translation? That means debris is going to go backwards. And that forms what we call the back sheared anvil. And that back sheared anvil tells me stuff. Here's the thing. I need the divergence more than the translation, and then I get the back sheared anvil. So the question then becomes, does anything change this? The amount of divergence. The winds aloft are the winds aloft. Now, obviously, something can change over the course of time, but just sort of in a thunderstorm's environment, what's going on? Well, mass continuity says that the amount of divergence must be compensated by some convergence down here and vertical motion in between. So the stronger the updraft, the more the divergence. That's so important, write it down. Stronger, let's go, the stronger the updraft, the more the divergence. The more divergence then tells you that I've got a stronger updraft. So when I've got really strong updrafts, I see better back sheared anvils. And that's why these things are so important. What do I see on the back side of the storm in the back sheared anvil? Because as that grows, that means there's so much divergence, the air actually goes into the strong upper level winds. Material from the cloud backs up into the wind. And that's kind of significant. In fact, there are some studies that say the more the divergence, the larger the hail, because again, the updraft is stronger. So if there's 110 knots of divergence, it could produce golf balls. If it's 150 knots, it could produce baseball size hail. So all that's important. Now that leads me to a little story here. And that story is, there was a time I was looking at storms and they were going up, and this is what they look like. All the anvil was going off in basically one direction, and I saw no back sheared anvil. And what that means with no back sheared anvil is that the divergence was less than the translation. So I thought, oh, there's not that much divergence. The updrafts are not strong. The problem with that thinking was that the winds aloft were like 150 knots. Very strong winds. They were so strong, even though I had lots of divergence, these winds were so strong, everything kept going all in the same direction. And notice I drew this updraft tilted, which means they're shear. Now there's something that is important to know, is that storms move with the mean or average wind of the cloud bearing layer. In other words, how this storm actually moves depends on how strong the average winds are from basically here to here. You could make an argument that it's really from the ground. But basically through this part of the atmosphere, what's the average winds? Well, if the winds up the anvil were 150 knots, how fast do you think these storms were moving? Answer, at the day that I remember that I'm referring to, was about, oops, let me erase that, make it right, about 50 miles an hour. That's a very fast storm. So we saw them, we thought, oh, they're not that strong, there's no back sheared anvil. And we were wrong. They were very strong, really strong winds, good divergence, strong updrafts, started to produce tornadoes, but they're moving away from us at 50 miles an hour and we were 20 miles from them. We couldn't catch them. We missed out on what we look for on storm chases, which are tornadoes, because the storm moved so fast, because I didn't identify the back sheared anvil correctly. And that's what this lab is about. Can you understand why there was no back sheared anvil? So that's some of the things that we have to perceive when we're trying to come up with this conceptual model of the thunderstorm. Okay. So I wanted to just give a little bit of an update on that, talk about how to do that question about the thunderstorms, and then the spiraling. I'll give you a hint. If you're going to do the spiraling, look at the last slide of the PowerPoints on the introduction PowerPoints, the first one that we have. That if you have a tornado, and definitely a tornado is rotating faster than it's going to translate, almost assuredly, then you're going to get swirl marks. It's going to back up on itself. And so when we look at the debris field and we see swirls, we know that. Now, last summer, I was evaluating storms on that derecho, these really strong straight line winds that went through. And there's a lot of damage where the trees were going in one direction. And the winds themselves were like 50, 60 miles an hour. But we saw evidences that the tornado had been there, which means some of the damage actually fell into the winds, or tree branches flew into the winds, which means that the rotation was stronger than the actual speed of the winds. And that's how we identified that there was actually a tornado. So that'll help you for the last question on the lab. This other one we'll talk about the question prior to that. So these are the essays to conclude the lab so that you understand why we're doing this, so that we understand that air moves in different ways and when it's all put together. And we can have translation, we can have divergence, and we can have rotation. And those are the ones that I really wanted to focus on this lab. So with that, this is a short lecture, but it should help you finish up that lab. Good luck with that, and I will see you guys at a later point. Thanks.